Yes, good morning to everybody. We'll start off uh, the fifth chapter. We have started from yesterday. So this is a very simple chapter, but again, it needs a lot of understanding. The fifth chapter called it the principles of the spectrum. So principles of spectrum, we call it as the spread spectrum communication systems. Very important, please keep in mind, a very important point, any communication system, whether it is analog communication or a digital communication point of view, three things are very quite important. The first thing is utilization of the bandwidth. Utilization of the bandwidth, that is allowable frequency of the channel efficiently. That means you have to use all the frequency at all the time so that what we can utilize, so that we can send the information. The second point is very clear. As less as possible, we should use the transmitted power as less possible, because since if you use a more power, then there will be heat dissipation factor either at the channel or at the receiver or at the transmitter. What will happen? There may be dissipation factor. Due to the dissipation, the information will also be lost, and also it increases the cost. That comes to the one of the part of your low power VLSI design factors. Please keep in, one is efficient utilization of the bandwidth of the allowable frequency. The second is as little transmitter power, and thirdly, what we call it as small areas. Fourth is exactly cost. These are the factors of the communication factors. In fact, when you come back to the communication point of view, since we are just focusing with respect to the communication point, okay, since we are focusing with respect to the communication point of view, that one is exactly what the principles of the spread spectrum of the communication system. The second is in the principle of communication digital system. The two factors are important. One is efficient utilization of the bandwidth. Second is exactly efficient, what I call it as efficient utilization. Second is using as less power as less possible. Okay, so that means the two factors is this, okay, transmitted power. So we are very important. So please mind it. The main objective of design of digital communication system over AWG channel is the efficient utilization of transmitter power and channel bandwidth. So look back here. So how exactly, and please remember the first very important fact is that channel coding. Let's give a channel coding. So when you go back to the digital communication system, information theory will be converted into a binary sequence, that is binary sequence pulses. From the binary sequence pulses, it goes to the what encoding. Whatever the information to be sent will be converted into the form, into one of the form, so that the rate of transmission will be rate of transmission. Generally, we call it as channel coding. Whatever the information, let us say 110, it will be converted to another form, 3 bit at one time or 2 bit at a time, and something like that. So as you transmit the message like this form, a number of what we call it as number of transmission bit at a time is more. What we call it as transmission rate is high. As we increase the transmission rate, less power is simple, because we are using one bit, one power. So when you transmit the bit together at a time, so same power is required for transmitting the same message. That's what exactly. So that by channel coding, we can able to reduce some kind of a transmitted power. Okay. Of course, utilization bandwidth is also very important. How the channel coding, what we call it as one important point called the code redundancy. What is exactly the code? What is exactly the through code redundancy? It absolutely it means, okay, code redundancy means absolutely it means okay, the using of the what I call it as using of the unwanted things, removing of unwanted things. Okay, so this is exact trade. Using this trade-off, because I told you the channel coding will help you to reduce the transmitter power. Of course, we have to utilize channel. Need to be trade off. That means we need to trade off the transmitted power and the channel bandwidth in the exactly what code residency. So let us take in AWG channel, as for the AWG, the additive wide Gaussian channel. So we have the transmitter, AWG channel receiver. R is equal to information, that is R. So information bit at the information rate at the input of the transmitter R. W is equal to exactly what channel bandwidth. BE, that is bandwidth expansion factor. B is equal to bandwidth expansion factor R of the channel coded with transmitted signal. Bandwidth expansion factor of the channel coded with. Okay, this is exactly we define. This is most important. Look back. This is exactly uh, bandwidth expansion. Here it is directly proportional to the width of the channel, or is proportional information rate of this. Okay, absolutely talks information rate. Important. If we increase the information rate, what will happen? We can reduce the transmitted power. Please mind it. How transmitted power is directly proportional to the information rate. At the information rate means number of transmitted per second. How much you're transmitting. For example, per second, if you transmit 1 bit, we need 1 sample. Instead of the per second, if you use 3 bits, same power will be utilized. So that means if you increase R, transmit power is also less. That means with the help of the BE, that is bandwidth expansion, that is bandwidth expansion factor B for AWE channel, W by R, the width of the channel, exactly here R, that is R bit rate, we can able to trade off these values, and we can utilize efficient utilization of the bandwidth, efficient utilization of the bandwidth, and also transmission power. So that means exactly here buying it. Look back here, very important. Transmission rate, okay, at the input of the power is WR. W is equal to what? Width and bandwidth of the channels. Okay, exactly. By increasing the bandwidth, if you increase B, the rate of transmission is also decreases. Okay, look back here. So that means if you decrease the rate of transmission, bandwidth expansion is increases, which means that width of the channel is also, that means using of the bandwidth is also get increases. That means as you increase B, width is also get increases. Okay, exactly. The rate of transmission is also decreases. Like, of course, I have mentioned it, transmission rate, absolutely, it will be transmission rate will be if we improve the transmission rate, we can able to reduce the transmitted power. But very important fact is that in digital communication, we have to use both the factors efficiently, depending upon all specific purpose. What kind of width of the bandwidth of a channel has to be, what kind of a transmitted power for transmitting the message has to be used, that is exactly BWR. So therefore, in this way, by increasing, so this means we need to trade off. Okay, exactly. So now, see, apart from that means B, that is the bandwidth expansion factor, is the most important designing factor. That means as a designer for successful communication, successful digital communication, okay, he has to use the two things. He has to keep in mind the two things in mind is that absolutely one is bandwidth, second is transmitted power. So he has to trade off with it, depending upon how much. In some application purpose, the transmitted power has to be used as less possible. Some kind transmitted power is not a viable parameter rather than the, but so it all depends upon what kind of a designer wants to look at. But then generally the PE factor is give the important factor to design of the AWE channel. In most of the practical situations so far, in all the kind of, that is in all, including what you call line communication, telephony, and all what you call satellite communication, almost the bandwidth factor is exactly 2 less than or equal to B. The minimum requirement B, good efficient communication system is 2 B, and greater than or equal to 5. This is the basic design absolute. See, this is one of the factor. Apart from this, there are two important factors as on today communication which influence the design. There one is exactly called multiple access communication system. What exactly it means? Look back here. Let us say this transmitter here. There is exactly the receiver. There's a transmitter and the channel and the receiver here. We are going to transmit the message from the transmitter. See, look back, let us assume that the transmitter that is a user, first user uses the only 1/4 of the bandwidth. That means it uses only 1/4 of the allowable frequency of the channel. The remaining 3/4 first. Instead of using 3/4, another user can use the remaining space of that in the same channel, okay, and transmit the same message simultaneously with other users. That means such kind of, we call it as multiple access communication system, sending of the same information at a different frequencies in the same channel at the same time. We call it as this. This is possible today because the technology exists. What we call it as one factor is TDM or FDM, that is time division multiplexes or frequency division multiplexes. That means different information will be sent in the same channel at a different instead of a time by utilizing the channel. We call it as TDM. With the different same, so many frequencies are insulated, so many signals are insulated in a one, as with a different frequency, because different frequency, now the signal will get interfered together, we can transfer. Such we call it as FDM, frequency division multiplexing. So such kind of a technology which you already studied in our analog communication subsystem. As of now, let us take. See, this is only this means multiple access communication. For such kind, when you use a multiple access, generally the bandwidth factor W by R is greater than 1. Okay, exactly. W for greater than 1. So this kind we call it as. Look back here. Okay, when you want to use, okay, exactly. Okay, when you want to use, okay, when you want a multiple communication, access communication use, what will happen? We need to spread this. We need to spread the so many information along the bandwidth of the channels. That means so many signals will be present exactly at the bandwidth of the channel. Okay, that's we call it as spread spectrum signal communication systems. I hope you got my point. Spread spectrum. See, this is one for multiple communication system. When you come back to here, okay, when you come back to here, what exactly another way? Let us say only one single wave, single frequency, that is single frequency signal that is contain information. I need to pass in the one channel. So it uses only one. Let us say it takes more number of a power, that is more number of power, that is transfer power. So I need to, let us say I need to decrease what you call it as R, that is rate of transmission R. When I decrease the rate of transmission, I told you that absolutely decreasing what? Transmitted power. So that means if I wanted to reduce the power, let us reduce this R by increasing the bandwidth. The same signal has to be spread across the bandwidth of the channel. This is also called as spread spectrum. These things. I hope you got to understand it. Two factors, spread spectrum for a single. Increasing the band, we can increase the bandwidth of the, within the bandwidth, available bandwidth of the channel, we can increase the what exactly. You can increase the bandwidth and decreasing the rate of transmission. Rate of transmission decreases, absolutely transfer power is decreases. So it all depends on the trade-off, okay? So in the multiple communication system also, when you take the spread spectrum, these things, I can spread the so much signal at the what exactly channel. Okay, each will have some spread along this bandwidth. It is also called a spread spectrum technology. Now look back here, another very important factor in the spectrum, what we call a pseudo randomness. See, whether you use a multiple access system or use a single signal to, or use a single system, increase the bandwidth. Okay, exactly, increase the bandwidth in order to reduce the transfer power, in order to reduce the what exactly bit rate. Okay, absolute bit rate. When you transmit the signal from the transmitter, let us say via AWS channel, it receives the receiver. It will, as we know that in a communication system, any part of the communication, it contain unwanted signal, what we call it as. When you come back to our specific purpose, what we're dealing with AWG channel, that's additive white Gaussian channel, there is a noise percentage that, okay, with mean is equal to signal value, variance is equal to noise spectral density, that is n by 2. That means that when you pass the signal, when you spread the signal along the bandwidth, in order to reduce the transmit for a single frequency information tanks, or even in a multiple communication system, we are spreading across so many signals along the bandwidth. Definitely, all this kind, any kind of this, will get channel, will get distorted or get corrupted. It is only because, as I told you to mention, that it is only because of there are external inflow factors. What are the factors which contribute to the noise of the channel? I mentioned so many times. The first factor is there is an interference of the signal. There is some signals is present, what we call it as, when you transmit the signal, that is exactly with some interference, we call it the channel noise. And secondly, when there is a parameter, the characteristic of the signal will itself get changed when you transmit. Absolutely, what we call it as phase frequency of the signal change depending upon the factor of the signal it get interfered, depending upon the type of the channel, depending upon the factors, so many factors, permittivity, permeability, and also radius factor. So many factors, the radius and the length, diameter. When you go for transmission line factors, you'll know. So these are the factors which absolutely get changed. That is absolutely we call it as that is a signal parameter. One of the important factors which is absolutely getting one of the important factor which is really get affected while of the signal while flowing through the channel, it is a phase or a frequency of the channels. So that means that absolutely some of the signal when you receive, whether it's a multiple communication system or the spread spectrum technology or a simple digital communication system, that is what we have studied, BPSK, QPSK, FSK, there is a content, some kind of a noise inside, some kind of a exactly noise will be present in the received signal. That means we can say some unwanted signal. There is an unwanted signal which is present, unwanted signal, unwanted information is present in the information signal at the input of the receiver. This unwanted we call it as noise. Please mind it, noise here always equal to randomness. So that means when as soon as you pass the information from the transmitter, either to spread spectrum technology, spread spectrum communication system, or multiple access systems, or everything, when you transmit the signal along this channel, there is a kind of unwanted signal. This unwanted signal due to the randomness of the channel while flowing from transmitter to the receiver, that we call as a pseudo randomness. So we must understand that in the spread spectrum, two important factors. What is spread spectrum technology? I mentioned it because if you use a single transmission line, single transmission signal, if I increase the bandwidth, I can reduce the rate of transmission because B is equal to W by R. R is a transmission rate is increases, rate of transmission power is. What is exactly transmission rate? Sending symbols per second is more. If I sending 3 bits at one time, what we call it as an MRS, when you studied it in MRA PSK, MRA QM, you're able to know that aspects of that. Okay. So when you come back to this, this is absolutely we call it as, okay, here in the spread sector, I'm going to look back here. Okay, here in this spread communication system, it expands bandwidth transmitted by a means of channel coding redundancy. I mentioned it. Redundancy means reducing number of codes or avoiding some manipulating the code. That is exactly redundant aspects you're going to use it. Why? Because for example, if you have 20 bits, let us say that information as a binary code, I need to send along with exactly by this. Okay, this is exactly called what you call it as spread spectrum technologies. Okay, so when you say 20 bits is there, I can reduce to 15, avoiding unwanted bits, or grouping one of the groups, grouping the number of bits as a one, so that I can transmit such we call as a code channel code redundancy. Now let's come back. As I told you very clear, model of a spread spectrum digital communication here. How it is? This is a channel modulator. There is a pseudo random generator. There is a channel here which has an impulse response CF. Which this is a demodulator. This is absolutely, this is the receiver. This is input to the demodulator. Channel decoder is absolutely this. Okay. So look back here. What exactly this is? As you know, the information sequence will come. Here, the redundancy of the coding takes what we call a channel encoder, and this goes to the modulator. This is absolutely the modulator here. Very important, make note here. The signal comes, which will be used as pseudo random signal. This pseudo random signal will be used for increasing the bandwidth, or increasing or decreasing the what transmission rate. So that means whatever the information will multiply, will be multiplied with so that in order to manipulate exactly the increasing the bandwidth, or depending upon what R is increasing or decreasing in accordance with the B is equal to WR. Once this information will be modified by PM, then this signal will be modulated by the carrier wave. That is exactly we call it as modulator, that as you know, as simple as. So channel code whose bandwidth or transmission rate increase or decrease with the help of what exactly pseudo randomness or pseudo noiseness. Once this bandwidth is bandwidth or random in accordance with the requirement as per the BEW by R, once get increases, and this information will be spreading across, will be modulated by what exactly carrier frequency, whose maybe depending on BPSK or FPSK, whatever you use it. In BPSK with the phase, and FSK is equal to what exactly the frequency. Okay, then this signal will be transmitted. Once this PN signal will be generated, then what exactly, then the modulated signals start to generate. As this modulated signals start to generate it along the channel, then at the simultaneously in the spectrum technology, PN sequence will be what exactly will be generated. As the signal is received, it will be multiplied with the value of what exactly PN sequence generated, which is absolutely same as the PN signal sequence generated at the transmitter. Please mind it. So here this will be multiplied, this will get cancelled out. What we call it as a despreading process. That means it's the opposite function nature of the what? The function generated by the PN junction. That is why we call it as D spread. Only thing you please remember, whatever the signal generated C of T will be the same as a C of T, and it will be. Then once this goes and demodulate as usual, will be multiplied by the carrier frequency. That means it extract the information as a very basic function. Demodulator will get back to this. Then once this the information will be removed from the carrier wave, then this will be converted to the binary sequence will get back. This is exactly called model of the spread spectrum technology. Very clear, everything has been explained. Again, same thing has been repeated here. And very important thing is how exactly, see, look here, I mentioned it. So as there is a kind of some information interference in the channel due to the interference of so many signal. If you use a multiple access system or in a spread sub technology, there are some kind of interferences will add it together. That is also get affected here with what you call it as bandwidth or a power spectrums. Okay, but bandwidth of the power or a power spectral density of the signal, which we will discuss in the later stage. So what are the factors with interference in the spectrum? Two factors which is contributing the interferences in the spread spectrum technology. Number one, what we call it as broadband. Second is exactly we call it as narrowband. What is exactly the broadband here? The signals, okay, exactly. The other signals are of the broadband in a signal, okay, exactly. And narrowband is the one where broadband signals are being passed in the long signal. The interference caused by the broadband, we call it as interference due to the broadband, and the narrowband is the one information due to the high range technology, the band occupied by the information, we call it as this. So what are the kind of the modulation techniques used? There may be PSK, FSK. PSK we call it as a direct spread technology. When you use the PSK when you use exactly PSK as the modulation technology in the communication system, we absolutely call it as what we call it as PSK. Then that we call it as a direct sequence spread spectrum technology. When you use the frequencies, and that means when you use the change the frequency of the carrier in accordance with the model, in accordance with the product of the PN sequence for the information, we call it as FSK, which is also called frequency offing method. Frequency get change of the carrier depending upon the information. That is why we call it as a frequency off. In this exactly PSK phases of the product of the PN sequence, the information will get changed. It is called a direct sequence spread spectrum systems. Okay, exactly. See, look back here. Very important here. Direct spread spectrum. This is one. As I mentioned, is the PN sequence generated at the modulator in conjunction with the PSK modulation to shift phases of the PSK signal pseudo random at rate that is integer multiple of the batch. Okay, R is equal to the information rate per second, TB is equal to bit interval, and BC is equal to channel bit width. Look back, what is exactly direct sequence spread spectrum? We call it as a DS. What exactly are the PN sequence generated after the multiplication, PN sequence, after the multiplication with what a PN sequence generated, multiplied with the information, where it enhances the bandwidth or it enhances rate depending upon what we require in accordance to the equation. B is equal to bandwidth expansion factor is equal to what? W by R. Okay, then this signal will be modulated by the PSK, some of the carrier waves by the PSK. PSK means absolute phase shift. The phases of the carrier wave will get according to the information which is contained the product of the information of the PN sequence. Okay, that is exactly, we have directly spread the signal to be transmitted along the bandwidth channel. We call it as a direct frequency spread. So R is equal to information bit, TB is equal to bit. This is the information to be passed, and this is look back. See, look back how this goes is. See, let us take, this is very important, please understand this. This is the data signal, whose amplitude here, whose amplitude the magnet plus or minus, this is the information. The bit interval TB of the data signal is this much TB. And let us say this is the PN sequence generated. As we mentioned, this will be utilized, which is we multiplied this, and the bandwidth rate of transmission power is, look back here. This is only, look back here, only 2 bits at a time, 1 and 0 in the TB. When I just multiplied this, I'll get back to this signal. Look back, the number of bits 1, 2, 3, 4, 5, 6, 7, 8, 9. That means 9 bits has been increased as compared. If I just transmit this alone, okay, exactly, The number of bandwidth absolutely less. So when you use the number of here, look back, when I increase the number of the bits, that is number of what I call number of cycle per second, absolutely you are using what exactly bandwidth will be increased. So that means this is the signal, this is the PN sequence generator, and absolutely this is the what exactly, this is the information to cross. When I multiply to this, what we call it, this is absolutely we call it as C of T, this is PN sequence, and V of T is the information signal. When I multiply this, I'm absolutely getting increasing number of a cycle per second, which we call it as what we call it. We can conclude that the bandwidth of the signal, bandwidth of the channel has been utilized since the bandwidth or the number of cycle per number of bits per second has been improved because of the PN junction, the PN sequence generated multiplied to this, and hence we can say that this is absolute bandwidth of the channel is increased. This is one of the main objects in this perspective of technology. Okay, so now let us say, now look back, the information is contained in a digital. The information digital signal I can mention as AN is equal to amplitude. This is G of T is equal to TF. That means that is as simple as vector sum, that is a convolution sum. That is because it has been constructed. The V of T is equal to output, which is given by this equation I mentioned it, which is absolutely what exactly, that is taking by unit impulse response at every moment. The output has been constructed in this pattern. Okay, G of T is equal to rectangular pulses of TB. Okay, so look back, very important point here, the rectangular pulses of, okay, exactly, each rectangular pulse of PN junction we call it a rectangular pulsar, with is equal to P of T, each bandwidth, each what we call it a time period, that is each time period we call it TC, where TP is equal to what exactly, this is the time period of the signal to be sent across this. Okay, so that means AN is equal to 1, this is the signal to be passed. We have constructed that is what we call it as V of T by taking unit impulse response of the signal to be transmitted, that is G of T, G is prefix T of T rectangular pulse of this. Okay, when you take V of T is multiplied by a signal from PN signal generator, so that means we need to multiply because in order to enhance the spectrum of this, okay, in order to enhance the spectrum of the bandwidth, okay, absolute, we call it as C of T is equal to summation N is equal to minus into the plus infinity, C of N is equal to P of into T. P is equal to what, each rectangle pulses in the sequence will then multiplied with what exactly, we multiplied with the magnitude of the PN signal. So C of T, that is a rectangle pulse, this is the rectangle pulses of the PN signal will be PN multiplied by the magnitude, as taking the simple response, unit impulse response of that, we'll get back to this equation. Okay, CN is equal to binary PN port sequence of plus or minus, PT is equal to rectangular pulse of duration, this. So when you multiply spread the bandwidth of the information bearing signal, whose bandwidth is approximately equal to R of Z, into the wider band occupied the PN generated signal. Okay, the spreading is okay, exactly V of T into CF. Okay, exactly here the spectrum spreading is illustrated. Okay, exactly, this is what the signal information to be sent. Okay, V of T, and this is exactly C of T is equal to this much. When you multiply to the both, we see this is TB, this is simple. When you come back to the PST, that is power spectral density, okay, when just this is this and this multiply to this, look back at bandwidth, this is the real signal, and once I multiply to this, the bandwidth is increased with a 1 by TC or minus of 1 by TC plus 1 by T. So this is absolute convolution. By using a convolution property, by using a spectral for a Fourier transform, we can get back to this. Okay, look back. So once this signal is come, this signal has to be transmitted after modulation with the help of the carrier waves. So let us say the carrier wave is equal to what? AC into cos 2 pi CT. When I multiplied this AC into cos 2 pi CT is the carrier wave, which has to be whose amplitude vary in accordance with what exactly V of T, and the resultant will get back to what, AC into V of T into C of T into cos 2 pi CT. Okay, exactly, the cos 2 pi CT is the absolute cos 2 pi CT the carrier whose amplitude varied in accordance with the what exactly V of T into C of T. So that means the resulting wave, this is exactly the analog signal we are going to transmit from the transmitter after spreading the bandwidth of the, in order to enhance the expansion of bandwidth, so that we can be able to get whatever we desire, either bandwidth expansion or reducing or increasing the rate of transmission as per the equation B is equal to W by that expansions. So that carrier is exactly here. Okay, it's absolute. Okay, exactly. In this, look back, C of t. See, when you multiplied it, the C of t. Okay, exactly here. Right. The figure C of t is equal to what you call it, it's 1. V of t is equal to AC into cos omega t. AC into cos omega ct t into plus t. Okay, exactly. So look back here. When you while looking this, look back here. This equation magnitude you have assumed this is 1 and this is 1. V of t and C of t magnitude is equal to 1. That is why we'll get back to the resultant wave or resultant received signal. Okay, exactly. We are transmitting the message v of t is equal to AC into cos omega here, but there is a 2 pi ct into theta of 0. This is 2 pi cos omega. As we multiply, the phase is also get changed. Okay, this is exactly we mentioned theta of t. So theta of t is equal to 0. V of t is C of t is equal to 1. In a similar, theta of t is equal to pi. That is what we call as phases get changed. Theta of t pi is equal to Vt of c equal to minus. Therefore, the transmitted signal is a binary signal in form of binary PSK. So, okay, understand the fact. So that means I am going to send V is equal to AC into cos 2 pi Ct, whose magnitude is varied in accordance with the V2 of Ct, which is a spread spectrum signal, not to requirement of V as for W or R of this. Okay, so that means absolute. This is the ratio. This is the magnitude. V of t is equal to when theta is equal to 0. So look back when theta is equal to 0. That is absolutely when theta is equal to 0. Look back here. When theta is equal to 0, the magnitude is equal to 1. That means exactly V2 or V2 V of t into C of t is equal to 1. When theta is equal to pi, that is absolutely opposite towards the 0. That is 180 degree. It has to the magnitude as we assume that what we have C of t or V of t is equal to what exactly minus 1. We'll get back to that. That is V of t into C of t is equal to minus 1. So this rectangular pulses of this, okay, exactly. The rectangular pulses, look, rectangular pulses absolutely used in the what exact rectangular pulses absolutely used in this exactly we call it as a chip. This each chip will have a what I call as a TC. Each chip will have exactly a TC. That is TC is equal to what? The chip rate 1 by C is equal to chip as one is that. So when you take this, LC is equal to bit interval of time by chip interval, which is absolutely TP by TC. Okay, absolutely, you got it. The point is okay, exactly here. So rectangle. Therefore, the transmitted signal is the signal in the binary VSK. Okay, exactly. So that means we got it. V of t is equal to AC into cos 2 pi Ct. This is a signal to be passed. But since we are multiplying the V of t, that is absolute A into cos 2 pi Ct. Cos of 2 pi Ct plus T of t is equal to this. Theta of t is equal to 0. V of t into C of t is equal to 1. Theta of t is equal to pi. V of t into Ct minus 1. This is exactly this is. This is the each rectangle pulses of the each rectangle pulse of the PN signal generated we call as a chip, and 1 by chip rate corresponding information. In practically spread spectrum LC is equal to but interval TB into the chip where chip L is equal to TB by TC. Okay, exactly. Right. So this is absolutely the signal. That means when you use LC by TB by TC, this is processing. You have to choose what is TB, what is TC. So you can, depending upon that, we can able to spread or increase the bandwidth of the technology. Okay. So let's come back to the another one, what I call demodulation of the DS spreading. That means that is a signal. So look back, what will happen in the spread spectrum, direct spectrum. This is a signal, let us say V of t, that has to be constructed from impulse response. That is going to multiply with what exactly? The PN sequence generated. Okay, exactly. The PN sequence generated, that is C of t, will be multiplied to that. We are able to increase the bandwidth. That is what we call it as what is spread spectrum. Okay, spread spectrum. Once it exactly spread spectrum technology will be utilized, then it will be we'll take one more carrier as per the PSK, whose amplitude will absolutely varies in accordance with. Then we are going to send the information by changing the phases of the value. Okay, so that we got it as V of t is equal to AC into cos 2 pi Ct. So that signal will be received. Now that signal, once you received here, that is R of t is a received signal at the receiver. Now demodulation technique. Two things has to be taken in the demodulation. The first fact is what exactly? Retrieve the information and get you the input converting. How the retribution? R of t. So look back is R of t is equal to what exactly? Or receive the signal. So what will happen here? This received signal will be multiplied with the PN sequence C of t. The C of t multiplied is, as remember that in a block diagram of the spectrum, I told it should be same at the receiver and the transmitter. And this will be multiplied with the C R of t into C of t. What we call it as, we remove the, what we call it as a de-spreading process. So that means look back here, what is expected receiving signal? AC omega t, the AC V of t into C of t into cos 2 pi ct into multiply. This is the received signal we do expect. Of course, I mentioned it. V of t is equal to C into multiplied the C of t is equal to what? 1. So that means we multiplied. When you multiply C of t will become C of t into C of t will become what exactly? Square. As you know, C of t TFC, as mentioned, we have used the PN sequence whose magnitude is always 1. So C of t square is equal to 1. That means we have AC into V of t into C of t. So V of t is the real information we need to pass. We have removed what exactly? PN sequence. That is exactly we call it as de-spreading technologies is exactly AC into V of t into cos 2 pi ct. This is absolutely the de-spreading process. Once this de-spreading process, absolutely we are going to multiply to the carrier wave in order to deduct whether it is the information is 1 and or. Once it deduct, and it will be taken over a time, because since we are sending over a time period TV, since we are sending the information as a level, and it goes to, as this is analog signal, as since we are dealing the digital communication, we need to be what you call it, take the sample as per the sampling theorem we are getting across the output. Very simple aspect here. Okay, simple. This is exactly demodulation is a deducting the information, sending the information after in the spread spectrum technology. We are able to deduct this simply. We are going to multiply C of t. This is the PN sequence generated at the what we call it at the receiver, which should be same as the transmitter. As we mentioned, that means we are going to remove C of t. Here this process has been explained, because C of t is square, which is also magnitude is 1. As since we use a magnitude of the C of t, this is equal to 1 exactly this. So that means here de-spreading process, it contains a prefix C, V of t into cos. V of t is equal to what exactly? This is the signal. Okay. So now this is absolutely mentioned. See, look back, very important effect of this spreading. See, as you told that interference, as you told that when you pass the transmission from along the channel, there is an interference due to the broadband or narrowband. I mentioned it. That means there is a, that is, see, look back, this is absolutely the receiving signal before de-spreading process, and this is I of t is the interference factor due to the channel noise inside. Let us assume that. So I of t is equal to channel noise. Let's say some of the interference signal along with this, that is, this is the signal, the AC V of t. Then let us assume that interference signal along these transmitting message, this is the signal, that is absolutely AC into V of t into cos 2 pi ct, as if the form A of I is equal to cos 2 pi. When this signal is absolutely added with this signal, there is a chance of what exactly? Spreading of the power spectrum may be increased, power spectrum may be decreased when you take the response of the systems. So that means possibly increase the power spectrum, most error, or possibly decrease the error. This is exactly the interference form. So now let us take, when you multiply, when in the de-spreading process, what we need to multiply the C of t into place in the power spectrum. When I multiply, this is absolutely what do you call it as, this is absolutely what, this is absolutely the interference multiplied to the CT. That means absolutely when you multiply to the C of t value, so it will multiply, the same I of t will come. That's therefore it increases spread. I tell you, because there is interferences is analog signal, the information transmitting is all analog signal, there is communication. This magnitude at a different point maybe get maybe added, subtracted, phase may be added and subtracted, due to which spectral density may be increased, may be decreased than the unexpected things. So due to which what exactly the interference, the power spectrum is given IC is equal to PIW. Okay, exactly. IC is equal to PIW. PI is equal to IA squared by 2. This is average power. This all thing is, look back, very important here. When this is power spectral power, this is average power. See, look back, when you substitute all this here is a very important power spectral density of the noise interference signal is greater than power of the what exactly? Greater power of the this greater power of the noise power of expectancy of the interference mainly depends upon the W by R. That means if you use W by expansion factor as if you use the W expansion factor is more, interference is also lies because I is equal to that is interference spectral density is directly proportional, sorry, inversely proportional to W by R naught. So that means absolutely, it means if you use spectrometry, you're also reducing the noise apart from increasing the bandwidth, apart from increasing or decreasing your rate of transmission bit. It is also contributed with the albino to reduce, it also contribute to reduce the interference. That's most important factor because none of the channel is cannot able to come out of it. None of the channel will not give the 100% cases as per the ideal expectations. So this is what probability of error. See, look back, the probability error of error is equal to probability error for detecting the sequence. Detecting probability error, how you define probability error of error is detecting the signals. Okay, detecting the sequence of spread circuit signal. We assume the transmission is transmitted via binary frequency signal within the interval. That means if we able to pass, okay, transmit the signal of the PSK within the time interval 0 less than or dt plus, we'll have a probability error. So that means there is no derivation as per your syllabus indicating. That means you should understand what is probability of error. Probability of error, detecting the information, absolutely detecting the information through the spread signal. We assume the transmission is transmitted via binary signal within the range. So tomorrow will be the last class for your unit 5. It will be completed. Okay, tomorrow time will be indicated. Bye.